So first off, before I start this video, thank you PE 2015 for your $25 donation. This is the microphone I'm using now to narrate this part of the video. Then I'll switch to the camera that's going to be without the microphone. But right now I'm going to keep this short and sweet. We're talking about number 2 and number 11. Post-tension bars in members 2 and 11 will not be grouted and will be de-stressed after main span construction is complete. Do not remove bars. Okay. So there's a few theories. This is for the post-tensioning of the transporter. That's not what it says. I'm thinking it is for since it's not going to be removed until both spans are complete, because it's saying that it will not be removed until this span is complete. Again, do not move to it will be grouted and will be de-stressed after main span construction is complete. Main span construction cannot be complete until it has additional post-tension members going in, the longitudinal post-tension cables. And that would be a total of 4 more that need to go into this deck, the canopy. So I think this was designed to counter the forces to strengthen this because of the shape of it. Number 3 is an odd duct. Very, very odd duct indeed. It's on a slight bit of an angle. I think it's creating tension going this, pulling between here and here, along with this one. These are some very unique configurations. Almost, I would say, upside down. That they were trying to do something upside down, even putting it back, the forces back into the canopy, which is, I haven't figured that out yet, so I'm going to leave that alone. But the next part of this video shows you in general how this works, and then you'll be able to play with it in your own mind. But what the wild card is, we don't know what the post-tension longitudinal forces are able to counter. Could the post-tension longitudinal cables, just 2 of them, could it support the entire span, 175-foot canopy span, without these members being involved? Could the bottom post-tension member support itself flat and level without any deflection, if you will, just by itself? And then could it also support the top canopy, the extra loads that are available? Could it take the extra load there and also the weight, the dead load of the diagonals? It's a thought. Now, is this just a plate, if you will? This post-tensioning here, does this just act to keep these forces into the canopy, and then directing the forces back down here? So this would act, so that this would then need support from the top canopy, sending it back down there. It's like a ultimate vicious circle here that can drive you crazy trying to follow this. With that said, we're going back to 10 and 11. So there's a thought that the images people share with me on the side, it's coming out. One guy says, he's an engineer, says it started by failure by the post-tensioning member kicking, and you can see it in the slow motion video, he states.
And the NTSB investigation into last week's bridge collapse at FIU, and it confirms much of what we first reported on Monday.
Yeah, late this afternoon, the NTSB said it's removing certain sections of the bridge for its investigation, the same sections where we showed you the failure began. When you slow down this dash cam video, look to the left at the deck of the bridge, the north side, and you see that? A puff of something, concrete perhaps, shoots out the end, just where the diagonal truss meets the deck of the bridge.
So this is where people are getting it from. First time I've seen this video where it was actually looking.
Obvious sign something was amiss. And then this. Now NTSB investigators are taking away what remains of that diagonal truss and the vertical support beam it met at the deck. Those 2 pieces, as well as the floor and canopy from that area, are being taken for examination and testing. They've also obtained tension rods and hydraulic equipment, like this jack seen protruding from the rubble.
Well, let's go with that. It's perfect. That's what I wanted to add. It looks like a lot more than 1.39 inches, besides the machine has to go on too. So it would be from here to here is what's going on. And the elongation would be measured in here more than likely with this tooling. And this would be butted there. Okay, let's move on.
We learned today that subcontractor had done similar work, called post-tensioning, on the south side of the bridge earlier. They had moved to the north side of the canopy and were more than three-quarters done all of their adjustments when the bridge failed.
Oh, they know they were three-quarters done. There's two there, there's one there, and so we're on to the fourth one. That's what they do, three-quarters. I hate percentages. It's terrible to do percentages. I can manipulate percentages so many ways, you know. It's just ridiculous. He doesn't know what percentages they were done.
Now, the original design stress adjustments to those diagonal trusses were completed before Southwest 8th Street was reopened to traffic last Monday morning, but something wasn't right. Cracking was noticed, and the engineer ordered more adjustments, and no one requested the road be shut down again when the post-tension work resumed. The chief engineer saying he did not think it was a safety issue. It was.
And a couple other people have written me also that it comes out the back end. They were already finished this post-tension member. They were working on this post-tension member. Now remember, they were only supposed to elongate this 1.3 to 1.49 inches, not a range, but one of these is A and one is B, and I don't know which one is which. But let's just say that this is 1.3, you know, we're so close. And with that said, we see that there's way more than 1.4 inches of elongation going on beyond the tooling. Look, we did not see that much sticking out of the bridge. No one saw that much. I'm going to show you a better detail of that number 11. So let's get to it. We're at number 11 and 12 here. As you can see, these are 2017 drawings stamped by Denny. Again, I think that Louis Berger made him do an update to, well, quite a few things, including adding post-tensioning to number 11, as we knew it was existing in the number 2 in the previous rendition of Denny Pate's drawings. Now, there's also things that people say, well, these aren't their working plans. All stamped engineered plans you can work with, unless they're disapproved. And then in that case, they'll get another stamp once they are approved. All right, so that's the way that works. And it's the latest rendering that supersedes the previous, that will supersede the previous renderings stamps. Now we have this here. This is the top, and that's the bottom. This is your strength of your seals. Here's 75,000. 75,000. Okay, so that's what this steel is capable of putting out. But with that said, VSL would have made the final determination. But let's figure that he talked to VSL, and they said spec 75,000 in here, and that's the reinforcement, and that looks like 65,000. All right, so that's the cage, and you don't want any conflict. So when the forces are applied, you don't want to resist inappropriately. Without he needs his cabling to have his post-tension rod to have the forces on it, not inadvertently taken into some steel, and then the forces being transferred right here. It needs to compress, put the compression on the member. Now let's talk about hypothetical. Could this post-tension rod hypothetically cause the member number 11 to buckle on its own, just sitting out by itself? Could it cause that? I don't think so. Even with the void in it, I don't think that you could make this 75,000. And you can simply do the math. You calculate the void, you do the area of concrete, the side, the dimensions, figure out where this location is, then the length of it, and you then do a factor on it. With that said, what makes it hard, you can do a general if that was right about here, but no, it's still going down and embedded in this much concrete. And when I say this much, this is about the 3 foot. Now at the top node, that's another game. So coming back to this drawing again, I just visited another drawing. This is the one that everyone's claiming that, obviously that's the one they were post-tensioning, that they saw slow motion video shows concrete shooting out the back end. That would imply that this had to go through 3 foot of concrete. But look at the path as it has to go through. It would have knocked off the inside of the bridge, the bottom inside of the bridge. This is the bottom chord, if you will. That path would have, you would see concrete fail inside here first before you would see concrete out here. Now it has to force 3 foot of concrete out. You wouldn't have seen a little crumb. You would have seen a huge chunk of concrete come forcing out. And it's from here to here. You would have seen 3 foot. A crumb you see coming out could just be this little piece here. When the bridge started failing, that little thing shot out. It's a crumb, all right? It's nothing. Let me jump on this real quickly. The blister bar above here, this was done after the canopy was installed. The canopy was installed after they had the uprights in, and that's per the images that they show online, the time-lapse. That's per the time-lapse images. The canopy was done second, and then the blister bar was added last. That creates a few points of a slip joint, and that would be this one and this point. Between this and the top canopy. This is obviously added to be flat, so it can take on the, right here, it can take on the 16-inch pipes. So it had a flat surface to anchor to. Otherwise, it has this radius, and that would just be asking for trouble. So they resolved that by putting a blister bar on top, and that's where they're going to put these decorative / resonance cancellation product in, the 16-inch pipes. Okay, so they can jackhammer a lot into that node, and we still can be safe now to some degree. Now this is just the wings to act as a gutter. There's your four post-tension members. Only 2 were applied at a time. As you can see, they jog. They come so close. They start off initially, then the path changes to go on the outside of the node, not alongside it. Parallel, of course, but not closer as it clearly could have gone. So this force also, though, even though this may look like it's going away, when you put tension on this, it's actually forcing this direction. Imagine that. So put a piece of string, a shoelace, or anything underneath your chin, and then put one hand high and one hand low above your chin, on opposite side of your chin. And now pull the strings outwards away from your body. And you'll see it'll have effect of raising your chin up. That's the same thing as this. As they pull it as they put post tension on this, it forces this way. So and the other side, the mirror side of this, would do the same thing. It would counter it. It would force this way, keeping the canopies arch. And integrity is what it would keep giving it integrity, ideally. But they were never installed, so we don't know if it could take. That's the worst part about it. We don't know. Now I want to address one more thing. That this is amazing. You know, this. If the engineers would come clean, if everybody would just be forthright and forthcoming, we could all learn from this. But in my opinion, I don't think they will be. That no one's going to just come clean on all of it where the mistake is. They clearly know where they made the mistake. They all think the engineering is good. FDOT thinks that thought that plans were okay. Denny thought the plans were okay. Louis Berger thought the plans were okay. And then you have VSL, who did the post-tensioning, thought the plans were okay. It was turned to the federal government, which the Federal Highway Department had to take a look at these plans. And I think they silently signed off also. So, and then we have this university that's a structural engineering college, if you will. They signed off. All right, C1, that's the post-tension members going through. I think we talked about this already. That was going to be the 2 members going through both decks. With that said, this bridge cannot be complete. The span can't be complete until you finish the 2 longitudinal post-tension members, which includes the other half of the bridge. I think this crack, or that looseness, if you will, of the of number 11 and number 11 got them freaking out. Now, people say that they were going to tension this. I just showed you a moment ago that was obviously designed to take tension off. So at one point, they were not detensioning at this point, because the detensioning doesn't happen until the bridge span is complete, as I just showed you above. And again, that kicking out, that would be amazing. Of course not. You would see a failure here first. You would see it shoot there, and they would have to go through all this concrete to see it kicking out. They're just seeing the failure after the fact, and you see that with the video I'm attaching. Let me add this. This is 1 foot of concrete. Concrete is tested pretty much 1 foot height and 8,500 psi. Let me think about that. Oh, yeah, it fails at 8,500 psi, plus or minus 10%, 500 psi. Okay, so we know the deck is 1 foot thick, not this section, of course. We know that without reinforcement, it's going to fail at 8,500 psi, plus or minus 10%, 500 psi. And we have this node on there that we're applying a load to. The node, I keep calling the node, the blister bar, sends the forces down this section here, and it's only 1 foot thick. It's not the end profile, which we see here at the end of the bridge. It's this profile that the load is being applied to. And remember, it has these voids in it, these unfulfilled, isn't that interesting? We're all unfulfilled, right? These unfulfilled voids. Unfulfilled. These vacant voids. This is where the post-tension members, the ducting, was going to go through. And they were not filled yet. So they were not applying. They were not contributing. But they were contributing a void, about approximately a 3-inch or greater void here and here. So when you add this compression, and over here also, here and here. When you start adding compression, this no longer has the counteracting forces to keep this bridge in stability, if you will. And the load that they're applying here only has to cancel out 8,500 psi in the canopy, and it only then can cause a crack. Once it causes the crack, everything, all bets are off. The bridge can't, the two remaining post-tension, the two only existing post-tendon members in the canopy then have to resolve this crack. They have to hold the load. But this post-tensioning device is still working at that point. And it starts causing the buckling after it cracks. Maybe they try to turn it off. It's too late. Game over. They try to stop it from still post-tensioning after the crack happens. This is what I'm thinking. After the crack happens in the canopy, the machine's still going. Maybe they attempted to shut it off. You show the crack deck is happening now. The number 11 can take the load. It starts to buckle. They shut it off. They don't shut it off. I don't care. I don't know which way that goes. All the forces then transfer down number 10. The deck was never designed to take all that load from this top canopy to then go onto one member, a single member, number 10. Number 11 is pretty much not contributing anymore, and it cracks the bottom deck, and not an odd place at all. The loads go to number 10, and let me address that real quickly. So as the load goes down number 10, we can see here there's no evidence in the drawings of longitudinal post-tensioning going down the center of the deck. It only had to defeat 8,500 psi deck with some reinforcement at the bottom of it. And with that much load on a canopy and the post-tensioning device still operating, as far as I would think it was still operating at that point, it was just concentrating the load onto driving number 10. So as this is post-tensioning, the loads, it cracks the deck because this is separate, and this is where it's also bonded separately. This is reinforcement only. So as it's driving here, it only has to make 1 foot of deck fail. It makes this 1 foot of deck fail through post-tensioning. This cracks. This still keeps ramming on. As it rams on, the load transfers down to here. We see it buckle. The load, once it starts buckling, this takes on the majority of the load. It's no longer in balance. This has the majority of the load. The forces from this column are then driven down into the center of the deck. And that's where it is, the center of the deck. And the failure happens right about here, I believe, which makes sense. If you do spans, unsupported span from here to here, would be about midway. So when it started cracking, the midpoint here would be the weakest point between these two. And that's where the crack showed itself. Not just here, but so if we don't get, so I'm hitting twice on you guys. So if we don't see cracking here, right here on the bottom deck, and we see it here, well, that's why. Then that means the deck held up, and I'm wrong on that part of the deck not being able to take it. But nevertheless, then the forces are between here and here. All of the top canopy, when I say all of it, a significant amount of the top canopy is no longer making it out to here and no longer making it down to here because of the post-tensioning. At that point, it loads down number 10. It's more upright. It loads down 10 once it starts buckling. Once it hits this, the loads then try to make it to here. And halfway between here and here is right about here, and that's where we get the defeat of the bridge. So let's look at this. This is where people are going to claim that this started, when they were post-tensioning, that this kicked out and this just caused a collapse. Remember, as the details show in 2017, they were going to remove this totally. There was going to be no load on it. So if this tensioning didn't cause a force to shoot this out, well, ultimately it did, but it did not cause the failure. All right, let's start it again, and I'll show you or explain something. Okay, as they're applying the load on this, at one point, I think the canopy cracked. The machine just continued operating, as I just stated. Continue operating. They probably try to shut it down. The deck was cracked. The machine just no longer had resistance anymore, so it could work. It could work in a faster capacity, if you will. They couldn't shut it down in time, or if they were even manning it properly. Well, I don't know about properly manning it. At that point, the machine just still kept working, and it came to that. It was all bets are off. This machine did not cause this buckling. It caused the cracking of the deck, is what I theorized. Once the deck was cracked, the two existing post-tension members on opposite sides of this, opposing sides of this canopy, could no longer keep a flat surface, a structurally flat surface. The loads were too great because it no longer had the concrete helping it bond, including the reinforcement. And this then took the load. Both of them took the load. This being on a more horizontal layout, it buckled. These forces came down here. It did not really buckle. It took the forces, and that put the load transfer from here, from this entire canopy, as the canopy failed, from here to here. And they split the difference pretty much. It wound up in the middle, but it appears where it found its weakest point was right about here once the load was transferred down to the bottom deck. So and I looked at this, there appears to be no punch through of this number 10 shearing through, which I think I made comment in another video that it could split the deck, crack the deck, etc. I don't think it did now. I think that the load did transfer and made it successfully. And at that point, the bottom deck could not take the load of the upper deck, its dead weight, and all the columns' weight on it also, including this action of this, and also including the action of the post-tending member trying to shorten itself. Okay, you can look for things in the back here and look for here, but first let's work on this. We got a break here, then we see post-tensioning, and then the load transfers down 10. This is this band that's left at that point. It transfers, the majority load goes here now of the deck, and since this is buckling, all the load is no longer transferring there. This is no longer a tension. It's more of a dead load deal going on, and crack. Interesting if it could be a tension crack. As I just counter myself, I think it's a dead weight crack, and here we go. Okay, so you can see the breaks here. There's no punch through. 10 didn't. You see this is flat. For 10 to punch through, this would have had to change shape. This would have had to change shape, and there's no change of shape. This looks like a change of shape there, though, as it goes, as this broke, and wow. It's ghosting, isn't it? It's just ghosting. I don't even see it. That's odd. Okay. So there we go again. Cracked deck, load transfers. You get your kick out, but not of the top post tension member, not the bottom one, the one they were working on. And unless you can tell me you would see a huge chunk of 3 foot of concrete coming out, it doesn't matter. It's not. It wouldn't have the. It would also have to move. It would have that post tension bar. We know now is coming this direction, as we saw in the failure. And if it was going, if there's nothing to stop it, to back it, reinforce it as the bridge fails, to force it to push through 3 foot of concrete. It's nothing there. I mean, you could say the node would be that force, but we have the node separating and pushing up, because as you saw in the well, I didn't put that video up yet. It's just rebarred up top. It's just a separate connection. Okay, and there's your secondary break, and again, no punch through. And this is totally intact. I would say it's totally intact, there's failure going on. And now we've got a hinge effect going on right here. Hinge binding. So it's going to break free. Same thing as your door in your house, where you can get hinge binding. So this guy is now broken free. This is just connected with some reinforcement. It's being pulled down with the whole gravity and its weight, etc. And there we go. And there's the, back it up one more time and call it a day. It's been brought to my attention numerous times that you guys really appreciate these videos. And I really appreciate you guys watching them and your feedback. You know, it's really nice to get some positive feedback and, you know, negative feedback if it can lead me somewhere. But if it's just trolling, that's no fun. Trolls will wear you out. All right, so the video here, I just slowed it down. This is reversing and going whichever way. And I appreciate you guys also chiming in when you catch on somebody kind of trolling and I let their comments slide, that you guys sort of gang up on them. That works for me. All right, thanks a lot for watching. Thanks for this mic.